Hey, math nerds. So what I'm going to do is I'm going to talk about convexity and convex functions. In particular, I'm going to prove that a particular function is convex. Okay, so let me get to the topic here. So how did I get to choose this topic? So right now I'm doing a course called a course in machine learning and AI, artificial intelligence. So in this particular course, they have this nice looking function called the cost function. So let me write down. It's denoted by J. J depends on two parameters. So W is the vector, P is a scalar, and this is 1 by 2m summation I1 till m W dot xi plus b minus yi the whole square. Okay, so this is the dot product, and there are m vectors. So let me explain what is x, the vector x, and the y's, which is also called as the outputs. So for that, let me just quickly write down. So x1, y1, x2, y2. You will see why I'm doing this. So xm, ym. So there are n vectors. So in machine learning, this is also called as the training set or the data set. Okay, so this is basically this training set is composed of the input. Input is basically, here it's a vector. You're inputting a vector, and this is the label associated with this vector. So this is basically you are training a model. So what you do is you give this training set to an algorithm, and the algorithm will try to learn from this training set. Okay, so for this particular input, the label associated is y. Okay, so and for this one, the label is y2, and so on. So what the algorithm will do is it will try to learn from this. Okay, so for this particular input, this is the label. For this one, this is the label, and so on. It will learn, and I'm not defining exactly what is learning. Okay, so it will do that, and what it will do is it will learn to predict correct labels. So any new input that you give in, which is not there in the data set, the algorithm will try to learn, and it will predict the correct label, okay, or the prediction of the correct label. Maybe, for example, let's say, emails, okay, whether to classify whether an email is spam or not. Maybe your input is, an email. Let's say you're able to convert the email into a vector format. Let's not go into detail how do you do that, but let's assume that the input is a vector representing an email, and y is the label associated with it. So, so the label here can be two choices: either the email is spam or not. Okay, so the algorithm will learn from this data set. So there are m vectors associated with m emails and the labels, and it will learn, oh, this is a spam mail, this is not a spam, and like that. And then it will learn to predict whether this particular email is spam or not. If you give a new input email, then it will learn to do that. So that's basically the training set or the data set. But the function that I've written here, it is basically called the squared error cost function. So let's denote this as cost function. Cost function is basically trying to measure how well your model is doing given the data set. That is, okay, I'm going into machine learning and AI, but I'll just skip through this. So the model is something which will try to fit to this data set. Okay, maybe in this case, maybe a straight line. So let's assume that you have the training set and you plot it in some kind of a space. Okay, let's say you're able to plot this in a 3D space or 2D space, and then the model is a straight line, then it will try to fit this collection of points, right? Okay, it will try to fit it. Fit, by that I mean it will try to be, the line will be such that, the it will be close to all these data sets. So basically, cost function is telling you how well this linear model, in this case, so this is the linear model, it's called linear regression, how that is performing or not. Okay, so let's get to convexity. Okay, so when do I say a function is convex? So if a function is defined from some set, say k, and if it's real value, this is convex, provided if you choose 2 points in the set k, okay, and also assume that for this particular argument, let's also assume that k is a convex set. Okay, this is a convex set, and if you take 2 inputs from this set k, then if you evaluate this particular value, so tx1 plus 1 minus tx2, this is less than or equal to t fx1 plus 1 minus t fx2. Okay, so basically what's going on here, and this happens for t in 0, 1. Okay, so let me explain what is going on here. So this is basically the definition of a convex function. So if you have a function f, let's say your k is along the real line, and if you take 2 points, x1 and x2, so if you take x1 and x2 in the x-axis, and this corresponds to fx1, this is fx2. Okay, so now what this statement is telling us is that for any point between x1 and x2, let's say this one, you can evaluate the function value. So that's here. So maybe this particular point corresponds to tx1 plus 1 minus tx2 for some value of t. Okay, let's say t naught, for some value of t naught. Let me denote it like this, for t naught, or t naught x1 plus 1 minus t naught x2, and then the corresponding function value is here. But the statement is implying that that particular function value is less than or equal to the corresponding point on the line joining fx1 and fx2. So the corresponding point will be this one. Okay, so if you just extend that point, the function value vertically on top, it will hit the line, and this particular point is basically is bigger than the function value. Okay, so that's all the statement is telling us. So pick any point between x1 and x2, the corresponding function value will be always less than or equal to the corresponding point on the line. Okay, and how do you figure that point? What's the function? I mean, what's the mathematical formula for that? That's basically the right hand side here. Okay, so whatever value of t naught or t that you pick to figure out this point, the same value of t you will use to figure out the point on the line. Okay, so you just have to plug that into this formula and get that point on the line. So that's all convexity is, I mean, the convex function is about. So basically it takes a convex shape. Okay, so it's telling you that this function is like convex. And now the question is, why do we need convex function? In terms of machine learning and AI, we need convex function so that the algorithm that we use to train the model is able to figure out the local minimum for this convex function. Because convex function, if there is a local minimum, then that will be a global minimum. Okay, what I just said right now, it's not relevant for this particular discussion because we are just going to prove that this particular function is convex. So this is the definition of convex. But if I need to use this to prove that our function j is convex, well, that's going to be a humongous task because j is 1 by 2m summation I1 till m w dot xi plus b minus yi squared. That's going to be a hell lot of tasks. So what I'm going to do is I'm going to state a theorem here. Maybe I can give a proof in my next video or in coming videos. So the theorem states that if you have a function, any function, let me denote it by j, which takes value in the real line, and on the set k is convex, okay, it's a convex domain, then and assume that all the second partial derivatives are continuous, okay, okay, I can say in mathematically j belongs to C2k. That means you can take all the second partial derivatives, even the mixed partials, all the second partials. For example, dou square j, dou w I j, right? For different indices I and j. So you can calculate the second derivatives, and they are continuous. Okay, if that is so, then if and if the Hessian matrix associated with J is positive definite, I will explain what is that, positive definite, then we say that then J is convex. Then J is convex. Okay, here are certain terms that I need to explain a little bit. So first, what is a positive definite matrix? So a matrix A, n cross n matrix, more or symmetric matrix, okay? Symmetric matrix is positive definite if it's a positive definite, provided if you do this calculation here, x transpose ax, so for any x not zero, any column vector x not zero, non-zero, if you do this calculation, if this is positive for all such x, then we say this is positive definite matrix, okay? Okay, that's the definition of positive definite matrix. And so we need to, so by looking at this theorem, we know that our function j is pretty nice. It's a really nice polynomial. And so all the partial derivatives can be evaluated. It's continuous. So only thing that's remaining is that I need to prove that the Hessian matrix is positive definite. So let's evaluate the Hessian matrix. So to evaluate the Hessian matrix, what I'm going to do here is I'm going to make it a little bit simpler. So J, instead of writing a vector, I'm going to consider scalar. So this time W is scalar. Okay, so, and our function is 1 by 2m summation I1 till m W xi plus y plus b minus yi, the whole square. Now, also I'm going to simplify a little bit here. So m will be 2, okay? So the m, so I'm just considering 2 data sets, okay? Okay, so I'm assuming that m is 2. So let me write down, let's keep that m there. And so m is 2, okay? That means I'm taking 2 inputs among all the n inputs. So I'm specifying that m is 2 just for, simplicity. I'm simplifying the case. Also, why m equal to 2? Because you have 2 independent variables. So 2 independent variables. So 2 is enough, okay? 10 variables, so 2 is enough. Okay. Right, now, so I just need to calculate the Hessian matrix for J. Okay, I have not defined what is a Hessian matrix. All right. maybe I should have a defined Hessian matrix before, then the simplification would have been much more, you know, much more justifiable, I guess. So let me write down general Hessian matrix. So a general Hessian matrix will be dou square j, so dou w1 square, dou square j, dou w1, dou w2, etc. Dou square j, dou w1, dou wm, and then dou wn, sorry, not m, n, and then dou square j, dou w1, dou b. All right. And then similarly, you can calculate the second one, dou square j, dou w2, dou w1, dou square j, dou w2 square, etc. Dou w2, dou b, and the last one will be dou square j, dou b, dou w1, dou b, dou w2, dou b, dou wn, dou square j, dou b square. Okay, so this is for if your vector, when your vector w is it has n components, so then the Hessian will be this, and your function j has one more. B is also an input there. So in that case, the Hessian matrix will be this monster-looking matrix. But now I'm simplifying the case, right? I'm saying it's just single variable. W is a scalar now. So in that case, I just need Hessian will be just so dou square j, dou w square, so just the first term, and then dou square j, dou w, dou b, and then dou square j, dou b, dou w, and then dou square j, dou b square. Okay, so this is for the case single w. Okay, so j is just a function of w and b. All right, now for this case, this is so, and so, and our j is wxi plus b square, right? Now let's do the derivatives here. So let's calculate the second partial derivative. So let's calculate the first partial derivative with respect to w. So in that case, by using chain rule, you have I1 till m wxi plus b minus yi, and then you take the partial with respect to w, so you have xi term. And okay, m is 2, so keep that in mind. And then let's calculate the partial with respect to b. Then that will be 1 by m summation I1 till m, and then wxi plus b minus yi. Okay, so that's here. Now if you calculate the second partial derivatives, so dou square j, dou w square will be 1 by m summation I1 till m. So you take the partial derivative of this one. So the partial derivative goes inside the summation, and when you take the partial derivative, it will be xi, and then there's one more xi here, so it's squared. Now second partial with respect to w and then b, that will be by m summation I1 till m. So when you take partial with respect to b, so that is xi. Okay, so that becomes this term. Okay, and when you take second partial with respect to b squared, that will be I1 till m, and that will be just 1. Okay, so if you do the thing here with this function, so you just get this one, and of course dou square j, dou b, and dou w, that is going to be the same as this case. Okay, these two will be the same, because these two, you can see the only difference between these two second partial derivatives is that I have flipped the order in which I'm taking the partial derivative. Right, first I'm doing it with w and then b, and here I'm doing it with b and then w. So because j is c2, it has continuous second partial derivatives, these are the same. Okay, now let's just write down the Hessian matrix. Okay, so 1 by m summation I1 till m xi squared, that's the first one. And then the next is 1 by m I1 till m xi. And then 1 by m summation I1 till m xi. And then 1 by m summation I1 till m1, which corresponds to this particular case here. Okay, so now my task is just to show that this is positive definite. Okay, positive definite. How am I going to do that? I just have to multiply a non-zero vector, so x transpose hjx. Okay, if this is positive for x not equal to 0, then I'm done. This is positive definite, and by the theorem, the function j is convex. So let's get on with it. So before that, what I'm going to do is I'm going to, instead of doing this calculation, I'm going to make it a bit simpler. So I'm going to do some things with this matrix. So what can I do here? Maybe I'm going to write the matrix as a product of two matrices. Okay, I'm going to attempt to do this. So m is 2. Remember, I had fixed m2. So m is again 2. Now, what I will do is this particular matrix, maybe I'm just guessing here, will be x1, and then this is x2, because there are only two. So x1, x2. And then if I do this here, then you can see that if I multiply x1 and x1, that's x1 squared. And then x2 times x2 is x2 squared. And then you add them together. So that will give you this particular quantity here, right? Right? You're getting that first once, because 1 by m is here. 1 by m is here. So that's good. So if you know matrix multiplication, then this is pretty easy. So I think this should be 1, 1. So x1 times 1 is x1, x2 times 1 is x2. So when you first multiply and then you add them, so x1 plus x2, and that is basically the second term here. Okay. Similarly, so this should be 1, 1. You can check that, all these, you're getting all these terms here. Okay, so that's good. So now our matrix H of j is this one, right? So this is pretty interesting, because I have written H of j to be in the form some matrix A times A transpose, right? Transpose means you interchange rows and columns. So what is X transpose HJX? So this is basically 1 by m X transpose A transpose X, right? And what is this? This is 1 by m. Well, this is basically, you can do this, right? So what is A transpose X? The whole transpose. You're taking the transpose of this time it's a vector here, because A transpose times a vector is another vector. So if you take the transpose, this is X transpose A, right? So basically this is A transpose X, the whole transpose, and then this, which is basically nothing but you're taking the norm square of A transpose X. Okay. So it's basically the norm squared. Now, what can you say about this? This is definitely a non-negative function, right? Non-negative. Now, the only thing needed is that I need to be sure that this is always positive if x is not 0. Now, how do I do this? Assume that A transpose x is 0. Okay. If it is 0, I need to prove that x is 0. That's the only case when this can be 0. If that is the case, then this is good, because in that means that, so if this implies x is 0, I'm done. I have done, the proof is complete. Okay, so is this true? Because remember, A transpose is this particular matrix here. Let me write it down. x1, x2, 1, 1, right? Well, because A transpose is made by, this is formed by, it's a function of the training set. Well, it is possible, because you need this to be convex. I think it is possible that you can choose this matrix in such a way that this is invertible. And in that case, you have convexity everywhere. In that case, if it is invertible, then that means this holds, right? This follows, okay? Because you can take the inverse of this, right? Let me just show you. So A transpose x is 0. So taking the inverse both sides, so then this will become x is A transpose inverse 0. So that's basically 0. So x is 0 in that case. So yeah, so this is indeed true. So it follows that the Hessian matrix of our cost function is positive definite, provided your matrix A that I have found is, you need certain things with that, like maybe it needs to be linearly independent, all the rows or the columns, but I think that is possible. So, but anyways, at least we have shown that this is bigger than or equal to 0, right? So with that, with the theorem, that this follows that the Hessian is positive definite, and it is convex. It is convex on the domain. Okay, convex on the domain. What does that mean? That means that the function is kind of like a soup bowl shape. Okay, right. So I think that's all for this particular video. And yeah, so I'll see you in the next video. Take care. Bye bye.